It's my pleasure to introduce Thomas Ken Magnusson. He joined RU a while ago in the bachelor program, degree mathematics and computer science. Then continued on to do his master studies here. Joined the group working on algorithms and permutation patterns. It's a group that's co-located here at Reykjavik University, University of Iceland, Dartmouth College, and Otago University in New Zealand. And Thomas is going to tell us about forced permutation patterns and their applications in the field.
Thank you. Okay. I'm going to start from the very beginning. So what is a permutation? So permutation is an arrangement of objects. So this is a permutation. And this is another permutation, since this is a different arrangement of objects. And of course, this is also a permutation. So we are just arranging some objects in multiple different ways. So formally, we say a permutation of length n is a bijection from a set to itself. And we write the permutations in the so-called one-line notations simply by concatenating the values of the each element, like so. As an example, these are all the permutations of length 3. We saw some of them before on the previous slide. And we can represent a permutation graphically by plotting the points where on the x-axis we have the indices of the permutation, and on the y-axis the values in the permutation. So for example, this graphical representation is of the permutation 42153. We say that two sequences of integers are order isomorphic if they have the same relative ordering. So if you have some two elements in one of the sequences and one element is greater than the other, then in the other sequence, the corresponding elements have to have the same relative ordering. Okay. And a classical permutation pattern is a permutation. And a permutation can contain a classical permutation pattern if there exists a order isomorphic subsequence of the permutation. Order isomorphic, that is a subsequence in the permutation that is order isomorphic to the permutation pattern. Okay. And we say that a permutation contains a permutation pattern, if that is the case. And otherwise, we say that the permutation avoids the pattern. So a permutation either contains the pattern or avoids the pattern. So for example, if we look at this in the graphical representation, we have the permutation pattern on the left and the permutation on the right. These highlighted dots here, this is an occurrence of the permutation pattern. As you can see, if we kind of like stretch this graph such that it forms the same kind of a figure as the permutation pattern, then we have an occurrence of the pattern. So 42135 contains 213. And a mesh pattern is a pair of a classical permutation pattern and a mesh, which is a set of integer coordinates that corresponds to these boxes on the figure. This is a more restricted type of a permutation pattern introduced by Anders here and another co-author of his, Brandon. And they can kind of describe, they have like more descriptive power than the classical permutation patterns, we could say. So a permutation can contain a mesh pattern. First of all, it has to contain the classical permutation pattern. So in this case, the permutation contains the pattern 213, highlighted here with the blue dots. And secondly, these shaded areas in the mesh pattern must correspond to empty areas in the permutation. So for example, this here is an occurrence of the classical permutation pattern, the points 213. But if you look at the shaded areas, the areas corresponding to the shaded areas in the mesh pattern, there is a point there. So this is not an occurrence of the mesh pattern, but it is an occurrence of the classical pattern. And of course, mesh patterns can contain mesh patterns also. So first of all, it has to contain the classical permutation pattern, 213, and the areas corresponding to the shaded areas in the pattern, the first pattern, must correspond to some shaded areas in the other pattern. Okay. So permutation patterns capture many of the interesting properties of permutations. They can kind of describe certain sets of permutations. And we are interested in these sets of permutations avoiding some permutation pattern. Or even more general, avoiding some set of permutation patterns. So each permutation has to avoid each of the permutation patterns in the set. So this is what we call a permutation class. And the set of patterns that the permutations have to avoid, we call them the basis of the permutation class. And this is the fundamental question in permutation patterns, considering the permutations that avoid a certain set of permutation patterns, and try to understand them, try to describe them somehow. And one way to do that is to simply enumerate all these permutations in the class. So we say that two patterns are coincident if the avoiding set of permutations are the same. You can see that this is a sort of an equivalence relation, and we can partition, well, basically all permutation patterns into the equivalence classes, into these equivalence classes. And what I will be focusing on here first is to try to classify, that is coincidence, classify all the mesh patterns. And what we did was develop the algorithm which we dubbed the shading algorithm, which automatically does this for us for mesh patterns of length 2 and almost 3. So since it's very technical and very long and describing it, well, I wouldn't have the time. I will just try to give you a simple example of how it works. So we want to show that these two patterns are coincident. That means that in every permutation that P occurs in, Q also occurs in, and vice versa. Okay. We will do it by simply considering these boxes in P, which are not shaded, but are shaded in Q. And we will show that in a very specific occurrence of P, these two boxes are actually empty. That is, they correspond to some area in every permutation that is empty, does not contain any point. Okay. So let's just consider the occurrence of P, where the point 1, 1 is as far to the right as possible. Okay. So in every permutation, we're kind of thinking about this in the terms of like every permutation. So in every permutation, we're looking at the occurrence where this pattern and the point 1, 1, that is the first point, is as far to the right in the permutation as possible. So if you think about the box 1, 0, it's either empty, that is the area in the permutations corresponding to this box is either empty, and then we could basically say that, well, this pattern here, P, the occurrence of it is actually an occurrence of this pattern here. Or it actually does contain a point. Okay. So what happens if it contains a point? Well, let's just pick a very specific point. Let's pick the point that is leftmost in this area. Okay, and we just kind of add it to the mesh pattern. Well, that basically means that this occurrence of P here is an occurrence of this mesh pattern on the right. And well, and let's consider this subpattern consisting of the points 2, 1, 3, 4, and 4, 3. There is the last 3 points here. And if you think about the mesh pattern that is contained in this area, it's actually P. But the original occurrence of this pattern P, corresponding to these red points here, is further to the left than this occurrence of P, which means that in every permutation where this is happening, this new occurrence of P is further to the right than the original occurrence, which is a contradiction since we assume that the original occurrence of the pattern P has the point 1, 1 as far to the right as possible. Okay. Which means that this can basically never happen if we pick this specific occurrence of P. So this case basically leads to a contradiction. It doesn't happen. We always have the left case here. And we can continue to do this for the second box also, and we would see that we would get another contradiction here. And this can go on for multiple steps, multiple boxes, and so on. And each of these steps that we perform, putting in the points, this can also happen in multiple steps. So this basically shows that, well, this pattern P, if we take this specific occurrence of the pattern P, that's also an occurrence of the next pattern here, which is also an occurrence of this next pattern here. And this pattern happens to actually imply the occurrence of Q because it has all the shadings that Q has plus one more. And therefore, this occurrence of P is actually an occurrence of Q. So what does that mean? That basically means that if P occurs somewhere, we can pick a specific occurrence of P such that it's also an occurrence of Q. Therefore, P and Q are coincident. So this algorithm, although it looked very simple, it's actually, there's a bunch of heavy machinery going on there. Can classify all the mesh patterns of length 2 and almost 3. There is this one tiny edge case, which we just, well, do by hand. But notice that we are talking about around 70,000 coincidence classes. This is just impossible for a human to perform. But like previous attempts at coincidence classification have been, well, there are some automatic methods, but one of the first methods applied were just using pen and paper and try to coincidence classify everything. Okay, but this is only the first part, and there's a key idea that we're going to take from this algorithm and apply elsewhere. So what the shading algorithm is doing is it's picking occurrence of the mesh pattern such that some point is as far to some direction as possible. Okay, so we call this a force on the point. We're forcing the point to be some point as far to some direction as possible. Okay, and more formally, a force is a tuple consisting of tuples of a point and some direction. A point in some pattern and some direction, that is. So we're basically saying here, okay, the first point should be as far to the direction D1 as possible. out of all those occurrences where this is true, we take the occurrences where the second point is as far to the direction D2 as possible, and so on. So we define a new type of pattern, of course, call them force patterns, which consist of a classical permutation pattern and a force. So to actually compare these different occurrences of the classical pattern, we're using the force, but how do we evaluate them? How do we know which is like the occurrence where some point is as far to the right as possible? How do we encode this formally? So we evaluate each of the points by the direction in which it is being forced. So this is happening for some specific occurrence C. So we're looking at each of the points of the occurrence and saying, okay, if it is being forced upwards, then we evaluate it as the value of the point. So the one that is furthest up would, of course, have the maximum value, and so on for all the directions. And combine this for all the points in the permutation pattern, we can evaluate each of the occurrences of the pattern. And we say that an occurrence of a force pattern in a permutation is an occurrence such that the strength of the occurrence is maximized. It is maximized where we basically order all the so we evaluate the strength of all the occurrences and order them by the lexicographical order and take the one that's maximal. That's the occurrence that we're interested in. I mean, these could be, of course, multiple occurrences, but those are actually the occurrences of the forced pattern. Okay. So one thing to note that is that a permutation contains a forced pattern if and only if it contains the classical pattern to begin with. Okay. So it doesn't actually add any restrictions on whether a permutation can contain a forced pattern or not. If it contains the classical pattern that is being forced, it will always contain an forced occurrence of the pattern. So these forced patterns are simply reducing the number of occurrences of the classical patterns. Okay. So we're especially interested in patterns that occur exactly 0 or 1 times. And we call them binary patterns. And a permutation pattern is binary with respect to some basis if it occurs 0 or 1 times in every permutation in the permutation class avoiding the basis. Okay. And it's important that these patterns occur 0 or 1 times, as we will see very soon, because this allows us to basically pick a unique occurrence of the classical patterns and kind of deconstruct the permutations using it. Okay, so a force pattern where the force is of the length of the pattern is a binary pattern. Why? If you think about, like, first we take some point that is as far to some direction as possible, and then we take the second point, which is as far to some other direction as possible, and so on for all the points in the permutation pattern, then if we do that for every point, we must have a unique occurrence. Okay. So if a pattern is not binary, then there exists a permutation of length, twice the length of the permutation pattern that has at least 2 occurrences of the pattern. Why is that? If we take some permutation pattern, take some permutation that contains 2 occurrences of it, and remove all the points that are not in these 2 occurrences, then that permutation is of length at most 2n. Okay. combining these two, we can actually check if a permutation is binary or not. And we can make a permutation that is not binary by adding force to it. So if we force one point, it might make it binary. You can check that. If not, we add more force. We force one more point in the permutation. Okay. Okay. So now we're gonna change the notation a bit. Previously, we were kind of thinking of these permutation patterns like so, like these figures, and we could construct the permutations containing this pattern by just throwing in some points there and kind of evaluate the whole points as a permutation. Okay, but now I'm gonna draw this a bit differently. I'm gonna put all the points, give them their own row and column. And these areas should of course be empty, since in the with the classical permutation patterns, well, they are in their own line. There's no point actually on the same line in the same row or column. But now we actually change the notation again a bit. We denote this by putting in these red dots, which simply says that there can't be any dot. There can't be any point in these cells. This is what we call a tiling. And these red points are what we call obstructions. Okay. But we can still do the same thing. We could basically throw in some points there and construct a permutation containing this pattern. Okay. And usually we draw them like so. And this is what we call a gridding of a permutation. A gridding of a permutation where you basically place them onto this figure. Take a permutation and place it onto this figure, and then we have a gridding of the permutation. And the permutation with its gridding is a gridded permutation. A permutation can have multiple griddings, and each of them are then a different gridded permutation. So these are two different things. Okay. Another example here of a tiling. This is a bit more complicated, but this kind of shows that tilings allows us to describe these permutation or these gridded permutations a little bit more better. The first obstruction here, containing 3 points, basically says that we can't have a 2, 1, 3 crossing between these 3 cells. Can't place a point in the first cell there and point in the next cell, and in the third point, it would not be allowed to have it higher than the first point. Okay, and similarly for the second obstruction there, we can't put any 2, 3, 1 across these 3 cells. But the green ones there are what we call requirements. We have to place points such that we form these patterns there, the green ones. So we would have to put a 1, 2 into the upper left cell. So one thing to note that, so if each permutation has a unique gridding on a tiling, then the number of permutations griddable on a tiling equal the number of gridded permutations on the tiling. Okay. So we could ask ourselves how many permutations can be gridded on a tiling. We could simply reduce this to counting the number of gridded permutations on the tiling. Okay, but why is this important? Well, we can basically represent permutation classes using these tilings. For example, this one here. This one represents the permutation class avoiding these 6 patterns. You can see that each permutation has a unique gridding on this tiling. I mean, there's only one cell. You would have to put all the points in that one cell. Okay. So if we count the number of gridded permutations on this tiling, we are essentially counting the number of permutations in this class. Okay. Okay, let's think about this class a bit. So each permutation in this class either avoids 1, 2, 3, or it contains 1, 2, 3. Well, in the case where it avoids 1, 2, 3, well, since all the other obstructions there, the 6 obstructions in the original tiling, actually do contain 1, 2, 3. They kind of become redundant. We only have to think about 1, 2, 3, and that's actually a very easy class. It's well known to be enumerated by the Catalan numbers. So we could kind of say that, okay, we can understand this tiling here. But on the right-hand side, we have all the permutations in this class that do contain 1, 2, 3. So we put in the green requirement there, saying, okay, each graded permutations that you put there must contain this 1, 2, 3. Okay, so here is where the force patterns, the force binary patterns come in. Since each of them has to contain a 1, 2, 3, we could just as well just place the 1, 2, 3 onto this tiling. Just have them as actual points on the tiling. Right? But you couldn't place any 1, 2, 3 on this tiling, since each of the permutations that are gradable on the tiling on the left could actually have multiple occurrences of 1, 2, 3. You want to pick some unique occurrence of 1, 2, 3, such that they only have a unique gridding on the tiling on the right. Okay. And by picking a forced occurrence of this of the 1, 2, 3, and adding the requirements, the obstructions needed to enforce this, to make sure basically that these 3 points actually do correspond to this forced occurrence, we have a unique gridding of all the permutations on the tiling on the right. Okay. So since each of these, well, let's say call them subtilings, what we call components, they are basically cells in the tiling on the right that do not share any row and column. So when we're actually constructing the permutations by putting in the points, we can just think of these cells here independently. Okay. Well, the one on the right here, far right, it's actually also well known, easy to enumerate. And so is the second one from the right. It's only this one on the far left here that we have to consider a bit. But this actually happens to be a tiling where we have actually placed a forced pattern again. And in the where we have actually placed the forced pattern of length 1, well, the point corresponding to the rightmost point in every permutation. So why are we doing this? Well, now we have a well understood structural description of this permutation class here corresponding to these 6 obstructions that I showed before. And using this structural description, we can actually compute the generating function using these leaf nodes here in this tree structure. By basically combining the generating function for each of the leaves by either addition or multiplication, we can automatically, given this kind of a tree, we can automatically compute the generating function. The generating function which enumerates the class. Okay. So, well, it all looks very cute and nice, but this is actually, everything is done by a computer. We have implemented everything, so this is all automatically done by the computer. So let's look at the results of it. In the top row, we have the ones that are the so-called non-regular insertion encodable. Those are permutation classes that are considered to be easy. We've shown that this algorithm of ours can actually do these classes. So what we have managed to do with the force patterns are the ones in the second row here. We have managed to do one class of length 2, 26 of length 3, and so on. And many of them, as you can see, were previously unenumerated by the algorithm itself without using these forced patterns. Okay. Maybe the most notable result is the class with the basis of length 2, recently done by Sam Miner. And you can see the simple or like simplified tree description of this class here, which is at the end only dependent on one class with a basis of length 4. Everything else is kind of well understood and easy. This is the same result as Miner got in this paper, but way simpler description of this class. And this is of course possible because, well, we have computers that just find this simple description for us. Well, actually, Miner had to did this all by hand. So some future work to be done. So we're only actually placing these patterns on one-by-one tilings. We're not considering the case where we have some requirements and arbitrary tiling and placing patterns into those cells. And we have seen that there's a lot of possibilities with that and cases where this could be very useful. And of course, the requirements currently are only used for these pattern placements, but they will offer a lot more than just placing the requirements themselves. We could play with them a lot more. And also pattern placements of crossing requirements. So if we have some requirements crossing some cells, we're not actually, don't know how to deal with that at the moment, but we've seen that there's huge applications of that with juxtaposing classes of juxtapositions of permutation classes. Any questions?
So now there's an opportunity to ask Thomas for a few minutes if you have any questions, and then after that there will be a closed session with Thomas and the committee. Ask away.
So maybe I can ask one about the, so thanks for a nice presentation, by the way. The binary patterns. So, or start with the forced pattern. So you had the underlying pattern was classic, are you saying?
Yes.
And it needs to be, it doesn't apply to mesh.
It could definitely be applied to mesh patterns, but then, yeah, it could of course be applied to mesh patterns also. Yeah.
But then when you move on to binary patterns, that only is interesting for mesh patterns.
Sorry?
Whether a pattern is binary or not is only interesting for mesh. Interesting question in mesh patterns. There's no classical pattern.
Yes, of course, no classical pattern is binary, except for when you have actually a basis that kind of makes it binary.
Right. Not looking at form, but avoiding.
Yeah.
But to determine if some mesh pattern is binary or not, you have some interesting ones that are not tied to a boundary.
Mm-hmm.
Still enough to check for there's a length twice the length of the pattern.
Yes, yes. I mean, we basically do the same. We just, yeah, basically the idea is the same. I mean, you take some permutation, and if it does contain two occurrences of it, remove all. Yeah, that's true. It's not very clear. I mean, yes, you would basically, yeah, you can't basically remove the point. So it's kind of unclear how high you would have to go to actually check this, but
the result applies for custom patterns when you also have some non-trivial force.
Yes.
Any more questions? I have one question. Open session. You classified length 2 and length 3.
Yes.
What do you think needs to happen before you push it to length 4?
A lot of money to buy big computers. That would definitely help a lot. But also, I mean, this simply blows up. What we're actually doing is we're trying to classify these patterns, and first you have to show that two patterns are coincident, but then for those that are not coincident, you would have to show that, well, there is some permutation that separates them. And that step for length 3 patterns went up to permutations of length 10. So you would assume for permutations of patterns of length 4, you would have to go, well, we conjecture that it's somewhere near n squared-ish. So you would have to probably go up to 16, 15, 16. And just that would take huge amount of computational power and time, of course. But if you, you could take the algorithm as it is now, and if you have a huge computer and a lot of time, you could just make it classify the patterns.
Let's thank Thomas again. And then we'll have a closed session. If anyone is waiting for Thomas, the closed session should not take more than 15 minutes.
The rest of us can have some cake because the third.
I guess we can take that.